for my personal benefit. Okay, hi everyone. This is my abstract that I'm going to present to you guys while standing and not from a sedentary position. This is the abstract that I'm going to be presenting today. It's kind of like, I guess we can consider it a prequel to what I presented for my midterm. It's same author as my midterm presentation, but instead of 2025, when I was 23 years old, this is when I was 7. So it's the exact same narrative. They're trying to find if metallicity affects the shape of the IMF. I used both of these in my midterm presentation. Over here on the right, it's just, our classic story of this cloud that's collapsing, and small overdensities that are formed from turbulence are gonna get more and more overdense because those are local regions of higher gravity. And then over here on the left, we have an initial mass function. And as I said last time, the hypothesis is that lower metallicity should result in a bias towards higher mass stellar objects, just because there's going to be fewer particles and molecules that have more energy levels, so the cloud should be radiating less heat in the form of, or it should be radiating less energy in the form of light. So this was the cluster of interest. This time it was in the Large Magellanic Cloud. I believe it's also called the Tarantula Nebula, which is a lot easier than 30 Doradus. I don't know if is okay. Is that like a reference to El Dorado, the city of gold?
I have no idea.
Okay.
I never thought about that.
Okay. Well, so I think for the entire time I spent working on this presentation, most of it was spent just trying to make sure that these are the same picture. I don't know why this was so hard for me, but like we have like that blobby cluster right there matches that, and then we have this matching that, and then that like swirl, and then for some reason I just couldn't believe my own eyes. But then we have like that little pair right there, and then pair right there. So it is the same picture. It was selected because the LMC is lower metallicity than the Milky Way galaxy. It can range anywhere between 1/3 and 1/2 solar. And then also, this was another active star forming region, which we always like to see. This is a lot of information.
Sorry, what are the wavelengths?
It was it F160? I forgot the filter, but it's like in the 1 point something micron, so it's near infrared. And then I guess just to be more vigorous, that square right there was what they were analyzing. This was what they got. To be honest, I didn't really look at the table or the plot in too much detail. It was really mostly the words that I was looking at more, but basically the only big difference here compared to the study that I presented last time is instead of doing a chi-squared photometric fit, they did a mass luminosity relation based off of one HST filter, and that's how they estimated their masses. And what they found was that there wasn't any major deviation from I don't know how to pronounce it. The IMF in red, saltpeter. Okay. So yeah, they were hoping that they could find some kind of flattening of the IMF, but they found that the slope is approximately the same down to 1 solar mass, which is actually different from what I presented last time, where they did find that low metallicity does appreciably change the IMF, but it's because this time, because they were imaging something further away and they were using Hubble, they could only go down to that 1 solar mass range, where our peak masses, when you look at all of our IMFs, are below 1 solar mass. So it's kind of like if you were trying to measure distribution, but you could only do like a tiny bit of the tail. So that sort of set the stage for the paper that I presented a couple weeks ago. Yeah, that's.
So remind me in that, so they do see deviation from something.
They found so.
In the previous one.
Yeah, they did find a difference, but it wasn't. They weren't comparing to that one. They were comparing to, I believe, it was the Krupa IMF.
Okay.
Actually, sorry, Chabrier. But yeah, they basically, I guess, like this was like their negative finding, and then once they got JWST, they went back and then falsified their own finding. They improved their mass range, so they essentially improved their sample size.
Okay, so the takeaway is there's no difference in the LMC.
In their small subset of what they could identify, that's right. They found no difference. But they did note in the paper that the IMF does increase towards lower mass objects, and they just weren't able to resolve those.
So do you want to say a bit about what you're thinking for the final proposal?
I mean, I'm still leaning towards like the archival proposal. I guess.
So going after another.
Yeah. So I mean, all this is telling us is that, like, you know, JWST like accomplished its mission in like allowing us to probe high extinction areas, as well as just being able to see lower mass things in general, which has been incredibly useful for studying star forming regions.
Yeah, so archival JWST.
Mm-hmm.
That sounds great. Maybe you could think about, so archival JWST will be, you know, at least in this type of regime, you know, just because it's so difficult to get time on it, I don't know if you'll serendipitously find an object for which the main purpose was not either.
Okay.
So, I mean, assuming I'm correct, if you find an interesting object where, you know, you then look at if you then like follow the thread and you don't find any publications on it, that would be interesting. But assuming you do, then the point about archival is to also think about a new analysis approach. So that's something you could think about, right? Like if you got some ideas from these papers you read about the techniques that they used, and something that you think could maybe target lower mass objects, or do a different way of, you know, differentiating between these different profiles, things like that.
Okay.